Okay, I'm recording now. So you can hear me, even though I can't hear me. And you can see the slides. Yi and Yi. All right. Okay, so we did it last lecture. I'm not even really going to introduce new content because we sort of finished last week. So what I wanted to do today, so I just went through all of the previous slides and I pulled out slides that I thought were important. So I just want to go over sort of the whole course in summary, just touching upon all of the highlights. And then as I promised, I'm going to show you some stuff in Python, like how to take some of the functional programming paradigm that you've learned, and I hope you've learned, and bring that back into the imperative space. And I just want to say, good job, guys. This wasn't easy. You had to do something totally different. This was more than just learning a new language, right? You totally had to change the way in which you thought about explaining things to the computer, right? And that was difficult. Think back to what you were trying to do on your first assignment relative to what you're doing now, and understand that that's a pretty significant leap, right? So you should be happy with yourselves. Yeah, I'm happy with what you guys have done. So good job, everyone, for sticking this far. I hope that the stuff that you learn in this course is going to help you in the future. And in particular, I hope you won't be afraid of recursion anymore, right? That is going to be a tool that you're as ready to reach for as a while loop or, declaring a global variable, right? And I hope sort of the fact that I made you do math proofs sort of sharpened your thinking and helped you with your inductive reasoning. I hope you now see this really direct association between doing recursion and doing induction, right? And how that occupies sort of the same space, right? So yeah, good job, everyone. All right, so in summary, let's just go over what I would classify as the most important parts of the year. So this is an extremely important slide, the one that warns us about not appearing on camera, although only one of you have ever spoke. Okay, so all the way back to the beginning. So we defined something called referential transparency. Do you remember this? So expression is called referentially transparent if it can just be swapped out with things that are equal for it, right? And you're doing this in your proofs right now, right? You're taking things and you're swapping them out for things that are equal to show that one expression is equal to another expression, right? And this is totally different than something that we could do in an imperative language. Imagine if you had a variable X in an imperative language, what are you able to swap that out with? Well, you don't know, right? Because that's a state-based calculation. So the proofs that you'd be doing in imperative languages would be totally different than the ones that you're doing here, because we're manipulating Haskell programs almost as if they are just genuine mathematical expressions, right? So remember, right, a referentially transparent statement is one that you can just swap out with things that are equal to it, and it will not affect the execution of your program. An expression that satisfies referential transparency is called pure. And so remember that this whole time we've been dealing with pure functions, right? Including ultimately IO was made pure, right? By doing some type of trickery, right? So we've been working in this system, Haskell, whose expressions are referentially transparent and whose functions are pure, right? So that was a very important concept, right? That was the driving concept of this whole course. So functional programming in this paradigm, right, is a commitment to purity, right? Functional programming is one type of style of programming. Can you name any other styles of programming, right? So there's functional, there's imperative, which is what you're used to. Can you name the sort of third other one, which is important? Okay, so object-oriented, I almost call that imperative programming plus codified state, but sure, we'll give that. That's not the one I'm looking for. William's closer with saying query, but what? Yeah, declarative. Right. So remember, in imperative, you're explaining to the computer how to do something. You're giving it a set of actions to execute, which converge on the answer. In functional programming, you're defining a set of functions and then giving it an input so that the output of those functions are the thing that you want to compute. In declarative programming, you're asking the computer a structured question, right? Like, who are the members of this class under 30 who have over 80, right? That's a question. That's not really an imperative or an instruction, right? So those really are the three programming language pillars: imperative, declarative, and functional. And we've been operating under this sort of notion of what referential transparency means in the functional paradigm, that equal means equal. And I hope you sort of now understand what this means, right? If you see something and it's equal to 2 at this function call, it's going to be equal to 2 at any function call later. I think when we use an equal in Haskell, it genuinely means, look, these things are totally identical. Lambda calculus, right? So we talked about sort of other ways of codifying information. And one of those ways was a lambda calculus. So because you have to think back to like before computers were even conceived, or like before computations were even conceived, like there had to be some type of agreement or some type of formal system for describing like actions, right, to a machine that would, and whose actions are sort of doing math. Right? And one way of doing that was through functional programming. Another way of doing that is through like the von Neumann architecture or Turing machines, right? So sort of the one that won are these Turing machines, which are state machines that can move between states on input with the additional capacity to write to a piece of tape, to read from a piece of tape, and to shift back and forth. Right? That is the universal description of a computer. Right? All computers are essentially Turing machines. No computer can compute more than what a Turing machine can compute. So the question is, if we swap out this fundamental model with a lambda calculus, what are we able to compute, right? And it turns out that a lambda calculus is equivalent to a Turing machine. And thereby we can compute everything that a Turing machine can compute, which is, the space of all problems that are currently computable by computers. Now, maybe it's a little bit off topic, but there are problems that fall outside of the space of Turing computable, like factoring composite integers, right? This is why we have like secure internet and like credit card transactions, right? That this is all of that internet security is based on the fact that there are problems that we cannot currently solve with computers. So that's neat. But the thing for us that we have to internalize is that doing computer programming in the manner that we were doing it with functional programming is equally as powerful as the Turing model, right? So there's nothing you can do with an imperative program that you cannot do with a functional program, and vice versa, right? There's no functional program that we can't also write in the imperative style, right? So this is sort of good news, right? Switching paradigms is not actually going to weaken our computational abilities. So what was a lambda calculus? Well, calculus generally is an abstract theory developed in a formal way, calculus, computation, right? A lambda calculus is a formal logic for codifying computations that boiled down to two things. And what were those two things? Well, we construct lambda terms, right? This is what we call abstraction, like x goes to something, or we can reduce, doing something calling binding, right? So one of the first things we did was bind things. And one of the last things we did was bind things, right? Binding was an important part of doing monads. Right? So we sort of came full circle with this stuff. And why did I teach you lambda calculus? Well, primarily to punish you, right? By forcing you to do fancy math, but secondarily, so you could actually trace Haskell code, right? So tracing Haskell code is a much different beast than tracing imperative code. Now, this actually brings me to a good point. In terms of your exam, right? Remember, you do not have access to the REPL, which means there are questions that I can ask you now that I was not able to ask you on your midterm, because if I asked you on your midterm, they'd be trivial. And those things are, what does the following Haskell expression evaluate to? And what is the type of this Haskell expression? Okay, so please right? Practice doing evaluation and typing. And in typing, please remember to derive class instances or you'll get it wrong, right? So just you have to be sure to like search for equals or other assumptions that are being made and derive those class instances. Like the exam is not very difficult. It's just sort of like wide and breadth. You're going to have to remember to do a lot of basic things. Okay, we also had to learn this difference between postfix and infix. So postfix is a style of function evaluation that you're used to. Well, it depends. So if you're using an infix operator like plus or minus, right, you would write sort of 2 minus 3. And that would be the infix notation. The postfix notation, you would sort of say minus 2, 3. Right? And we've been sort of moving in between these two styles of representation for function calls in Haskell. So let me ask you this. If you have an infix operator called f, how do you convert that into a postfix operator in Haskell? Right, so instead of saying x, f, y, that's the infix, how do I convert that to postfix? Yeah, Metis has it right. You take that infix operator, you put brackets around it, and it becomes postfix. Oh, sorry. Yes, becomes postfix. How do you do the opposite? And how do you take a postfix operator called G, and how do you make that an infix operator? Exactly. You put these little backticks around it, so you can always move between one or the other. If you have mixed computations, right, with infix and postfix, how do you figure out which operation is going to execute first? Right? What gives you the order of precedence in terms of infix operators? Like if I were to say 2 plus 3 minus 1, right? How would you figure out which happens first? What can give you information about the infix or postfix precedence? Someone must remember. Precedence and associativity information is what Kenton Lamb says, but specifically, where does that come from? Can you see my REPL? Yep. What I'm searching for is this, right? You just ask for information about the operation at hand. And remember, right, down here, it's codifying a bunch of information, right? So this plus is an infix operator, which is left associative with priority 6. Right, so don't forget that you can always ask for info about these things, sort of to unpack ambiguity about order of operations. And these are always questions that like reliably are on every single programming test. It's an easy one to say. How does the following expression evaluate? Even though any non-student would just say, I don't know, just put it in the computer and it will tell us. Types. Okay, so types are super important. And in particular in Haskell, like this is a system with a very strong typing system, right? It won't even let you go, it won't even let you execute unless things pass the typing system, which is not true for programs like Python, which basically let you pass around anything, or in C, which has typing, but you know, it sort of is agnostic to like what is in memory, right? You can look at the same block of memory with different typing glasses and see different things, right? I can look at 64 bits as ints or characters, right? So Haskell is really saying, look, right? These functions are going to be set up in such a way that if you're telling me you're going to give me an integer and you don't, I'm not even going to allow you past like the initial execution, right? So this is a strongly typed system. Types, broadly speaking, are just sort of like sets, right? So the integers are the set of all natural numbers plus the negation of natural numbers. Int, right, is the set of all machine integers. Bool is the set of two things, false and true, right? And that's how we were reading this bar here as OR. So we set some data, it's a Boolean, and the data is comprised of either false or true. And we learned that types always have capitals, and concrete types are types like this bool, which don't require other types to instantiate them, like maybe or ethers, and that these concrete types are denoted by this sort of pointer or asterisk, right? So if I ask for the kind of bool, what is it going to spit back at me, Haskell? Remember, we have these different, we have kind and we have type. So the type of bool, I think bool doesn't have a type, or its type is itself. But what is bool's kind? Oh yes, Lyndon Wells is correct, right? Pointer, right? The kind of type is simply a concrete type. All right, so I want you guys to be very confident with typing stuff. So just make sure you get some practice inferring types. And go ahead and put that on the Piazza, right? Try to trick each other with typing things. Okay, currying. So currying refers to the nesting of multiple functions. So in Haskell, how many inputs can a function take? Like, what is the maximum number of inputs that a function can take in Haskell? Anthony Estelle says 1. Does anyone agree with Anthony? Lyndon Wells says yes. So you are correct. Those who are not sort of maybe abstaining from this vote, this is a critically important thing about Haskell. We do not have the capacity to define a function of 2 variables that goes to 1. Right? We can only define functions that take 1 variable and return another function. But this wasn't a problem, right? Because we could simulate functions of multiple variables by doing this currying, right? So a function that takes 2 variables to 1 variable is sort of equivalent to a function that takes 1 variable to a function that takes 1 variable to a constant, right? And the process of doing that, or like this style of evaluation, is called currying, right? Where we can go from where this function, which is really one that takes an integer, to a function which takes an integer to an integer, is equivalent to sort of having a bivariate function, which takes 2 integers to an integer, which would be this style, right? So what we normally do in Haskell is something called currying. But what we sort of do in other computer languages and in math itself is sort of this uncurried version, right? Taking tuples to constants. But nonetheless, you can go between these 2 styles in Haskell. There is a command in the prelude called curry and one called uncurry, which allows you to sort of convert between these 2 forms. But by now you should be used to sort of working in this format. I wonder how many of you are now going to be irritated that sort of the other languages you're working in aren't typed. You can't readily get typing information from them. Okay, so be sure that you can convert between these curried and uncurried styles. There's definitely a question on your exam about converting between one and the other. Let's just do some examples just for the hell of it for uncurrying. Right, so as I said, right, this is the curried version. So you can always take a function which has been written to take tuples to something and uncurry it, right? Sort of to get it into Haskell. You could also do this, right? So here's a function h, which takes 2 functions, 2 variables, x and y, and adds them, right? So this was from a long time ago, trying to understand how stuff like this can work. So the thing I want to just emphasize is, remember, like, this evaluates first, right? So this is not, so some people still make the mistake, and even I do, right, of going to the outside one first, right? You have to bind from the inside. So this is going to actually take 1 and bind it to x, right? So what the first evaluation step here is actually going to return a function h of y is equal to 1 plus y. So I just like to think of it as the things that are like closest to the function get gobbled first, right? Where h is eating its way through left or right. There's the uncurried version. It's sort of boring, but this is not boring, right? How to uncurry something, right? To uncurry something means to take a function that goes from type 1 to type 2 to type 3. And when we uncurry it, it should return this function, which is a function that takes a tuple to a constant or to a concrete type. And so note that you have that in the prelude. Here's currying, which is going the opposite way. This is all sort of stuff that you should know. But if we look down here, what does it mean to curry something? Well, that means to take a function that takes a tuple to a concrete type and returns, right, a function in its curried form, right? That goes from A to B to T. Type inference. This is something super important, right? That Haskell has a type inferring engine, which is sort of not something that's universally true of languages. So this means that I can give, and I sort of never called it this, but every function, like when you type, what is the type of f into Haskell, and it spits a type back at you. That most general type is called the principal type. So you guys have to be good at determining principal types of functions. So Haskell is always going to infer like the most general type that it can. If I say f of x is equal to x, like the identity function, it's not going to say, well, this is an integer function, right? Because that's going to be the identity function for any type that you care to give it. And so for stuff like this, if I'm adding, right, f of x, y is equal to the sum of x plus y, and I ask for its type, it's going to say, I'm this type, right? A function that takes a to a, right? Which is weird in itself. So let's look at this. Why is this a to a instead of a to b to c? What happened here that like made it so that x and y had to be of the same type and return the same type? Right, Maddie's is correct, right? This addition operator says, look, I'm an operation that's defined on class instances which provide addition. And one of the rules of addition is that you can't like jump into a different set, right? I can't add two numbers and end up somewhere else. So this is called like an additive group for those of you who have taken group theory. But yeah, this is interesting, right? That it can say, okay, look, this function's most general type, because I'm adding, is first you need to give me a type for which addition is defined, right, which is more broadly a class of numbers, right? And then provided that you've given me an instance of number, right, then I'm going to give you back this function which takes two numbers and returns a number. And so maybe we can appreciate this more like at this level, because like back then we were just sort of grappling with what types were. Right now we understand a lot more about Haskell. So like stuff like this should sort of be making more sense. But like this is interesting, right? Like how Haskell does this type inference is like a whole subject area in itself. You can also get types of sort of partially evaluated functions, which shouldn't be a surprise, right? So if I give it one, one actually is just a number, right? This is interesting why this wouldn't go to sort of like an integer, right? Because if we think about this, like which one is this? Is this a machine int, an arbitrary sized int? Is this a float? Is this a fractional? Well, it's all of those things. And so that's neat, right? How one is in a superclass called number, which is what is indicated by this, right? So one is just a type P, where type P is a number class. And there's this sort of way of binding, or I shouldn't say bind, I should say, well, forcing something that's polymorphic, right? Sort of one can be of many types, but you can say, no, treat this like an integer and read it in, which, I've had to use a lot in your sort of testing. Type classes. Okay. So this may have been new, right, to this notion of a type class. But as I said, if types are just sort of collections of objects, then a type class is a set of sets, and the inclusion into that type class is based upon providing certain operations or properties. Right? So if a type provides addition, then it gets to be an instance of the number class. If a type has the biggest element and smallest element, then it's a bounded class. If a type has a string representation, right, then it's of showable class, right? So in these senses, so again, the vocabulary is like this. Right? You have sets, you have type classes, which are sets of sets. So if you're a type of a class, you are called an instance of that class, right? So instance and element of sort of be swapped out here. Right? But that's sort of what you have to keep seeing, right? Sets of sets of sets of sets. If we look at info for bool, it's going to tell us, right? So bool is a type of exactly two elements, right? False and true. But bool is also an instance of sort of classes, and it's an instance of many classes. So it's an instance of equality. So as soon as you use equal, you're going to have to be of equality type. It's also instance of ordered, of enumeration, show, read, and bounded. Here's an interesting question. If you're ordered, do you necessarily have equality? No, yeah, I don't think so. Because you can have partial orders, right? So if you have binary trees, you can partially order them based on their height, for example. But there are many trees with the same height. So yeah, just be careful there. I think if you are bounded, are you necessarily ordered? Ron says yes. Ron, you're wrong. I made the same mistake. That's a mistake I made on the midterm, right? Assuming if something's bounded, then you're also ordered. You would think that if you're bounded, you're ordered, but you're not. And again, it's because of these partial orderings. But that was a tough question. That's one even I screwed up. Class constraints. Okay, so this is when you want to like define a function, but you don't want the principal type to be as broad as the inference engine would imply. So you can actually state in your function definition that the type that you're using is actually an instance of the class. Right, so you should be used to stuff like this, where we say that if your type A is of class C, then we can infer this type. A goes to A. And you can also do multiple instance declarations. You just have to sort of put them in these brackets. Is that generally true? Do I always have to put them in brackets? I forget now. Anyone in the chat know if I can drop these brackets? I guess we can just try. Let me see. All right, so let's define a function foo. Let's say that we have to have an ordered type A that goes from A to A. And foo is undefined. Okay, that's going to work for sure. Okay, let's try to do two things now. Let's say this is both bounded and ordered, and that should work. Okay, well, now let's try taking off the brackets. No, okay, so it doesn't work without brackets. So this here, I suppose, is always going to be a tuple of class constraints. And then from that tuple of class constraints, or sorry, I guess n tuple of class constraints, you can derive your typing information. Overloaded. It's not a term I really use very often, but a class with more than one instance, or a class with more than a type with more than one class constraint is called an overloaded type. So we're mostly dealing with overloaded types. Because if we don't have instances, we can't do very much. Here's a question. How many functions are there on the most polymorphic type, like of A? And how many functions can we have that go from A to A? with no class instances. Good job. One. Which one is it? Identity. Yeah, good. And I hope you understand why now. Like there's nothing that you can do on a type that won't force it into some type of class instance, aside just like writing it there. We can have these combinators. Like if you remember what these combinators were from lambda calculus, we could start playing. If we allow ourselves more inputs, we can do things like just, permute order. But it is interesting to note that given a data type, you can actually count the number of possible functions. I probably should have defined function again, but okay. Do you guys remember what the definition of a function is? What can't a function do? Or let me state it like this. If f of x is a and f of x is b, then what do we know about a and b? Same. Yeah. You can't have like f of 1 go to 4 or 5, right? It has to pass the vertical line test, if you will, right? Which really only makes sense on real valued functions, but it's the general principle is sound, right? If you give a function a number, or if you give a function a value and it spits back a value, that value has to be invariant, right? To being given the same input, right? Which isn't true in imperative programming. You may have a void function which returns the time, which is going to return something totally different each time. Incidentally, could we have a function that returns time in Haskell? Now that you have learned a bunch of stuff? Yeah, using monads. Well, in particular, using the state transformation monad, right? If you give me the state of the world, right, which presumably would include the current time, right? Yeah, sure. Why not? Mathematical induction, right? I kept having you guys do inductive proofs. You may be wondering why. Ron gets what now? What do you get, Ron? Induction or monads, or both? State of the world as an input. Good. Okay, so back to induction, right? I made you return to something you may have thought your math professors were teaching you for a lark, but this is basically like recursion. I still strongly feel that like doing these inductive proofs should have given you some clarity about writing a recursion, right? Just so you understand that it's like not magic, right? Recursion works, induction works because of this statement. So again, if you have any predicate, right, that's just a transformation on the natural numbers into true and false, right? Which means that any predicate which is enumerating some type of property, right? This n could be made isomorphic to any sort of data type that you want, right? I'm not only giving properties on the natural numbers, right? Then this statement holds, right? So that is to say, if you want to prove for every m that some property m holds, it is sufficient to demonstrate this, right? Namely, that the P naught is true, right? There's at least one thing at the bottom which is true. And if PM is true, then PM plus 1 is true, right? And if you can satisfy these sufficient conditions, then this is true. Sorry. Is induction something now that makes a little bit more sense, right? Especially now that we've like actually done inductions and turned them into recursion, like directly. Right? I talk of this sort of a blockist example. Is there anyone in the class for which sort of induction sort of makes a little bit more sense now? All right, I'll take it from Ron. Good job, Ron. Yes, Lyndon Wells, good. Like in all seriousness though, like I hope this like doing some inductions sort of helped you understand that like recursion isn't magic, right? It's like climbing a ladder. And as long as you have the bottom rung, and as long as there's a rung to reach to every time, then you can walk the whole ladder. And you can improve your recursion now too. Okay, so that was sort of the basic induction, right? And the reason this is basic is because you're only moving from like one step to the step directly above it. So for structural induction, you are assuming that sort of a whole, like a possibly infinite amount of stuff is true underneath you. You're not just going from m to m+1. You're going from m minus 1, m minus, you're assuming everything behind you is true in order to establish the truth to something next. Right. So in particular, you have a I've asked you to do a tree induction on your project. Right. So you should have something like base case are all trees with one node, provided that I don't think you can build an empty tree on your project. If it was the empty tree, then you just go for empty. But then you just come up with some type of partial ordering on your tree, like depth, for example. And you say, okay, let's suppose the property is true for all trees of depth n. And then I'm going to construct a new tree, and I'm going to show that this new tree has the same property, right? And if you do those things, then by structural induction, you've shown that all trees, right, will have the property that you're trying to prove, right? So it's just sort of like induction plus, but it's sort of the same idea. I gotta say, like the induction proofs like improved dramatically, right, over the course of the semester. Function composition. Okay, so if the only things that we can define in Haskell are functions, then the ability to like combine them is super important. And let's just remind ourselves what function composition does, because the order, it depends who you ask, which way you define this. But for us and in Haskell, if you have a function which goes from type A to type B called G, and a function which goes from type B to type C through F, then f dot G, or f composed with G, is going to give you a function that goes from A to B. That is to say, you take A and you give it to G, which gives you something from B, which given to F gives you something that goes to C. And so this is sort of the picture that you need to remember. If we ask for the type of what the composition operator is doing in Haskell, well, it's just going to do exactly what I said. Give me a function which takes B to C and a function which takes A to B, and I'm going to give you back a function which takes A to C. Now, realize that these brackets can't be taken off, right? Because this is saying, no, you need to give me a function, and you need to give me a function. If I take them off, then you're able to do these partial evaluations. So here's an example. If I have a function which just doubles something and a function that adds 1 to something, this would be a great question to ask on the exam, right? Like, what does this evaluate to and what does this evaluate to? So when I do this, it's sort of the same principle applies. It's always the function that's like the closest to that get, oh, sorry, no. Am I getting confused? F dot G, did I do this wrong? Oh, no, I didn't. No, everything I'm saying is correct, right? You always go from the closest functions to the closest values, right? So G gobbles up 2, and that becomes 3. And then that 3 goes to F and becomes 6. And the same thing's going to apply here, right? So F and 2 get bound first. So F goes to 4. And then 4 goes to G, and that becomes 5, right? So the reason that I can permute these things here is because A, B, and C were all equal. It's not going to be generally the case that you can permute the order of these function compositions. Geez, I got to pick up the pace. Point-free style. Okay, so we have these function compositions. And you notice here that they both had to take input, but you don't actually need to include this input on either side. Right, so here's just something called the point, but point-free means just don't write this. Right? It's not necessary, because we can say functions are equal to functions. Right? We don't have to say f of x is equal to g of x. We can just say f is equal to g. Right? And often it's the case that this is how things are written. So just remember, right? I can have something, suppose I want to double something and sum it. I don't have to say double sum of x's. I just say, okay, double sum is sum doubled, right? But you got to be careful. So, so I make this mistake. You can leave the bracket off. You can leave the bracket off here, but if you put the X back, if you're not using the point free style, then the function composition has to have brackets around it. All right, so just recall, there is definitely a question on your exam with asking you to work out the nuances of this. List comprehension. So this is the ability that's not unique to Haskell to generate lists using sort of like set constructing style. Right, so you can say, generate me all of the squares taking X from the set 1, 2, 3, and you get 1, 4, 9. Right? This is also something that you have in Python. Do you have this in Java? Who's Java programmers? Can you do list comprehension in Java? Oh, I thought one of you would know. It's been a while since I've programmed in Java. Well, you can definitely do it in Python. List comprehension is like a feature of most modern languages. This pipe symbol in this case is not read as or, but such that. And this arrow is read as drawn from, right? So you read, I want the set of X squared such that X is drawn from 1, 2, and 3. So X is going to step through these numbers and just evaluate here. You can do nested list comprehensions. You just got to sort of be careful about the order that they're being taken. Right, so this example is going to illustrate the order. So all the ones have shown up first. Oh, sorry. 1. I don't think Java has a nice syntax for it. Okay, so no list comprehension in Java, or at least no natural nice list comprehension in Java. So back to this. So notice that all the 1s appear first, then all the 2s and all the 3s, which means that we are exhausting lists from the end inward. Right, so you pick 1 from here, and then you pick A, and then you pick B. And if we put another one, would be exhausting from the end. Right, so if we switch the order here, you'll see that we go A, B, 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 right? Or 1, 2, 3, 1, 2, 3. We're exhausting from the end, right? Even though, right, the order hasn't changed here. So just take note of there's like this nuance, right? If I give you 2 list comprehensions, you're exhausting from outside in. Primitive recursion, where I'm sort of going to take the opportunity to talk about this outright thing once we hit tail recursion. Okay, so primitive recursion is basically the recursion that like you do naturally, essentially. So if you just have a function f and it has a base case and it has like an inductive case, right? That's primitive recursion. Right? If I do factorial and I say f of 0 is 1 and f of n is equal to n times n minus 1, that's primitive recursion. What I mean by outright is just like constant, right? You can't at like your base case do another recursive call. Like otherwise we're talking about like a sort of a larger thing. So when I say outright, you should be like interpreting this as constant, like you put like a number there, like you've stopped. And this is important if we're actually talking about the memory model. Well, it becomes more important in tail recursion. But that's what I mean to say when I say outright. Can any of you suggest like a better word for this than outright? It was what was used when I was learning. Like now I sort of appreciate that it may not be the best or like the most sort of descriptive term. Non-referentially. Any other ones? Maybe I should just say like constant, concrete, an instance of a concrete type or something like that. Yeah, it just should be a number, possibly arithmetic. I'm not sure. I'll have to give that some thought. But by outright, I mean like you just have you have a stopping point, right? You're done, right? It is something that's computed that we can just throw. So more generally, we have or gave a linear recursive definition. So a linear recursive definition is a function which calls itself only once. Can anyone give me an example of like a simple non-linear recursive definition? Like factorial is linear, Yeah, exactly, Ron. Fibonacci is not. Right. So when we start talking about these non-linear recursive functions, you're going to need a tool called sort of dynamic programming, which is recursion plus caching, which if we have time, I'll talk about. But linear just means you're going like you have one line, right? So you're like build up a stack, or you wind and then unwind. Right? If you didn't have linear, you'd be like winding as a tree, right? And this becomes disastrous, right? Because you're doing sort of like an exponential number of computations at each step. Okay, tail recursive. This is something I've been asking you to do over and over and over again because it's important. Because this is one way of taking a recursive algorithm and turning it into something which is still recursive, but doesn't require unwinding or doesn't require like generating a stack of instructions to wait, right? This is basically doing a loop, right? I've heard from many people that this is, I'm most comfortable programming tail recursion. Well, that's because it's basically what you would be doing in the imperative language. Like the reason that tail recursion is important is because if you, geez, it's hard to navigate this using my camera, but if you have a memory location in memory, right? If you have a function which is doing tail recursion, it only needs that single block of memory to execute, right? It has its instruction set and it's just overwriting one cell of memory. And eventually that one cell of memory is going to be holding the answer, right? So in terms of like compiler optimizations, writing in tail recursion is like real good. Okay, so in tail recursion, what you need to do is define an outright base case, right? So please read that message I wrote on Piazza about this tail recursion using average, right? I saw many solutions which are based, I saw many solutions which essentially is just doing a tail recursive sum and then cheating by dividing it out. You can't do that, right? The base case really just needs to like return answer, which is why I asked to do the primitive recursion, right? So you did a primitive recursion on average, you should have deduced the generalized pattern there. And then it's up to you to take that generalized pattern and just sort of like eliminate the unwinding. Right? But this is quite important. Right? So you can take this into your other classes, especially in C programming. Right? Once you guys start doing operating systems, you're going to need to do this type of tail recursion for things like piping. Because if you don't, it gets real messy real soon. A lot of the operations from the REPL are going to be like naturally recursive. Higher order functions. So this should be something you're totally comfortable with now that perhaps you're uncomfortable with at the beginning, right? And that's the notion that like everything in Haskell is a function, right? Functions can take functions, functions can return functions. And in particular, there are some, like the name of the game in Haskell was always doing stuff and realizing, you know, we've been doing this a lot. Like, why don't we try to like generalize the pattern out and then call the pattern? And we were able to like simplify our code by like a lot by sort of using higher ordered functions. So what were the important higher ordered functions? Well, mapping. So what does map do? So given a function, A to B, and a list A, you're going to list B. Right. And with this happens quite a bit, right? So you can map to the list of the first 10 numbers 2 times. And what was this called again? Right, the fact that we could like partially evaluate these infix operators. This has a particular name. It was called a section. Right? That's called a section. Should maybe I don't know how many languages have sections, but I thought that was a pretty neat feature. But anyway, so we have this map, right? That was the one high ordered function. And it was an important thing, right? Because it ends up being structure preserving, but we'll talk about functors in a second. Zips, right? Zips is when you take 2 lists and then you combine them in such a way that you get all the tuples back. Right? And we are truncating to the shorter one. So this is another higher order pattern that happens all the time. Zip with, right? This is actually what I think zip should do naturally, but zip with just does a zip, gets the tuples, and in addition to that, applies a bivariate function over them. So I can take zip with and add, and then you're sort of getting what we may call sort of like a pointwise addition. Right? So if we zip with 1, 2, 3, and 4, 5, 6, we can get 5, 7, 9 back. Right? And again, we're just truncating on each list. But this is a very useful higher order function. Filter is a higher order function, which is quite useful. So I always forget if filter should keep the thing or drop the thing. And in Haskell, when you filter over some predicate, that predicate is saying the thing that you want to include. Right? If we didn't have filter, would that be so much of a disaster? Is there like an easy way to write a filter using like a list comprehension? Yeah. Right. So using a list, if we wanted to filter out members of a list for some predicate P, right? So suppose that list is X's. You can just say, list X such that X is taken from X's, comma, PX. Right. And that essentially becomes equivalent to a filter. Now, we have filter because filter works over more general types, right? It works through anything that's, traversable or numerable or foldable. But in any case, right, what we have to remember about filter is that you're keeping the things that you want, not discarding them, or sort of somehow always want to reverse it. In other languages, filter is called select and remove, which may be more descriptive. All right, so you can do things like filter this string for all letters that are greater than or equal to A. And you get this back, right, mainly because the capital letters are ordered ahead of the lowercase letters. Folds. Okay, so folding may be something that you're new to, but this is when you have a list and you want to sort of keep applying a bivariate function, right? So if I said, like, what's another way we could define sum over a list of numbers, a fold would be appropriate. So we just have to remember that there are two types of folds, a right fold and a left fold. And they do basically the same thing, but with a little nuance, which ends up being a super important nuance. So the way I remember which way is which is the right and left indicator on these folds tell you which side the brackets are going to stack. Right? So here you see all the brackets are stacking to the right. And you immediately have your base case. So that's how I remember how folds should work. So on the right, everything should stack to the right? All the brackets and then the base case. So if you have some type of infix operator, bash, which is an actual Haskell code, a right fold is going to do something like this. So if we could look at our left fold, what I said is going to be true as well. All of the brackets should stack on the left, and then you have your base case, and you just sort of take something that's a list and you're returning something that's a scalar. And so you can apply any bivariate function over this. But folds are going to be very useful for you. In some languages, they're called reduce, but you may not have that base case there. And we'll talk about this when we head to Python. We're almost there. Signaling adversity. So recall that we really want to define total functions in Haskell all the time. Right? There's this difference between throwing an exception and throwing an error. Right? Throwing an error is fine, right? Because I can catch errors and handle them. An exception like dividing by 0 is not fine because that just totally terminates everything, right? The whole game is over. Right? So if we want to define a function, which may mathematically be not total, like 1 divided by x, then we just use this maybe data type, right? Which essentially just adds nothing, right? You have all the things in your set, your type, plus nothing. Right? The problem is, as we've learned in Haskell, is that often when we define a new type, we end up having to have these decorators, right? So as soon as we start using this maybe data type, right, then we're going to have to start pattern matching in and out, right? There's nothing and just a, but this would have been enough, right? So I think next year I'm not even going to do, what was the other one? Either? Yeah, either. Because either is essentially sort of not giving you any extra functionality over nothing, aside from the fact that you can use left to throw actual error messages rather than just throwing nothing. But like, fundamentally, it's not really that different. So just remember that you have maybe and either for handling errors, and that the non-enforced agreement among Haskell programmers is that left is used for errors, right? Because right is right. Higher kinded types. Okay, so we just talked about maybe and either, but maybe and either can't really be a type until you give it a type, right? So you can have a maybe int or a maybe string, but you can't just have a maybe. Right? So maybe would be of not a concrete type. It would be of type asterisk to asterisk, which says, given a concrete type, I will give you a concrete type back. And so here are a bunch of concrete types like int and bool and char. And in this case, we're reading these double colons as has the kind rather than has the type. Right. So this is useful if you're sort of working with derived types, right? Types that you've created that take types, and just to help you work out your typing errors at the beginning. Functors. Okay, so this is when stuff started getting interesting, perhaps, right? So we talked about a map, and we sort of started realizing that map was like over a list was just sort of an operation that reached into the structure of the list, changed the things inside of the list, but didn't actually affect anything on the outside of the list. And we realized that, well, actually, this could be something that could be generalized to anything with structure. We have lots of things with structure. Trees have structure. Like I may want to change the values of the leaves, but not touch anything with the tree. Or I may want to reach into a maybe and just change what's inside the maybe without actually changing the outside of the maybe. Right, so we had this notion of like structure preserving operations. And a structure preserving operation is called the functor. And what's a functor? Well, it's just a class. Right, so it may have been sort of confusing to like introduce these functors, applicatives, and monads, but remember, like one of the first things we did was talk about class instances. And sort of class instances made sense, right? It's like, oh, okay, you're just saying that my type has to provide some functionality, and once I provide that functionality, then I'm allowed to be a member of that class. And functor is just a class, right? So given a type which provides a map, which is a structure preserving operation, then you're a functor, provided that the map that you've provided satisfies some rules, right? Which was the new thing. Even though, like, if we dug into it, I'm sure addition and all of that stuff also has to provide rules, right? So summarize, a functor is a type is an instance of a functor if it provides this fmap operation that satisfies these rules. And we are able to mathematically demonstrate that the map that we've defined follows these rules. And in fact, I think I've asked you to do so, right? Which is interesting, right? Like, because you should, instead of trying to prove something is a functor, it's an informative exercise to like try and write a functor which types properly that nonetheless doesn't follow these rules. It's not that hard. Like, consider okay, so the name of the game is to choose a functor, is to choose an operation which is structure preserving, right? So suppose I try to define a functor over lists, which just reverses the list, right? Does that satisfy this typing? Yeah. Okay. Is it a functor? No, right? Because the identity doesn't work. Right. So there's an example of like something that I can make, which will type correctly as a functor, but nonetheless won't satisfy the rules for being a functor. Yeah, river should be a functor. Yeah, it should be a. You have to fact check me on that one. Have I reached into the structure? Maybe I said something wrong. Maybe what I defined was like something that's not an applicative. Okay, fact check me on that one. Or let's think about this. Did I reach into? Because that is structure preserving. But then what is the map? No. Yeah, I think I may have. Okay, but anyways, it's an informative exercise to think of something that would be would type correctly as a functor, but nonetheless not satisfy the functor rules. I think you can work in a reverse somehow. I'll have to think about that one. I shouldn't do these things off the cuff. Isn't there only one definition for every functor? Yes, that's. I'm not sure actually. But the point is, you can define like an arbitrary amount of functors that type properly, that nonetheless aren't functors because they don't satisfy the rules. Well, yeah, it is structure preserving because like it's a list of the same size, right? The outside hasn't changed, right? Some properties of the structure haven't changed. Like I can come up with a functor that just like negates everything on the inside, maybe. Like I can have something that types properly that doesn't actually like do anything. Like if I just negate, yeah, like give, okay, so maybe here, this is a functor that will type properly, that nonetheless will fail as a functor. Map anything just negates its input, right? And then the identity is going to not work. Right? Yeah, ignoring the function, right? Just at fmap, ignore the thing that you're giving me and just negate everything, right? That for sure is not going to satisfy the ID. A functor that maps everything to the empty list, but that is going to change the structure. Right. The point is that the length of the list should be invariant, right? The bare minimum, right? But I think, or like replacing everything in the list with 0, right? That will be a functor, but that definitely won't satisfy stuff like this. Yeah. Applicative classes. Now it's harder to get a grapple upon like what applicatives are generalizing, because really they're like this in-between step between functors, which sort of are very clear what they're trying to do, and monads, which are clear about what they want to do. But an applicative is the space where things like zips exist. All right. So again, it's just a class instance, right? It's just a type which provides pure and this applicative functor which satisfies the following rules. And so if that's your level of understanding, that's fine. Okay, and then monad is just again another class which has this bind operator, right? And this bind operator becomes quite important because there's this, you can't negate everything would require an extra constraint in the type signature of fmap. Well, you certainly can return a constant, right? Any constant. Anyways, you should think about it, right? Find a type, define a functor which types properly. That's not a functor. You should be able to do that. Yeah, I don't know where I think the reverse example may work to fail as an applicative. Anyways, yeah, think about it and someone report back on the Piazza. Yeah, I have to think. And I still think returning some constant would do it. Hold on, let's go back to what Ron was saying. You can't negate everything, would require an extra constraint. But suppose, so like we're not working over this constraint as it's written here. Like if I wrote a functor for an integer list, for example, then all of these would be ints. Right? I'm not saying write like the most generalized functor. I'm saying write a functor for like any data type that you want, write a functor. Right. So I think if we dumped in here integer list, like that would be fine. Right. If I had a function that just ignored everything and negated. Right. There's a natural definition for what the fmap should do, right? It's obvious, but like we just don't do that. Right? Doing anything else essentially will give us a structure preserving operation that will fail these functor rules. Yeah, like maybe, just saying everything goes to 0. Right? That would technically type, right? Because you just give me any integer function, I ignore it. and they take you from list of ints to list of ints where, everything, like nothing has changed, right? The structure is still there. Okay, so back to monads. Like the thing that this allowed us to generalize was there's always this problem with like what order do things happen? Like there are only brief instances where order matters. And one of those instances is where we're doing function compositions, right? Function compositions always allowed us to order at least mappings, right? G first, then F, right? So monads generalized this, which allowed us these brief periods of time where we could say, sequence some actions in the following way by just generalizing function composition. Like that's what a monad was doing, right? It's just a generalized pattern that says, let's take X to the following set of actions, which takes Y to the following set of actions, which takes Z to the following set of actions, right? Which allowed us to retrieve values X, Y, and Z in an order, right? So we have this definition for monad with these monad laws. Okay. Then we took this notion of a monad and applied it to this very particular type called a state transformation. And the state transformation is just basically allowing us to remember one thing. And how we generalized it here was that the one thing that we're allowed to carry is like an integer. And as soon as we're allowed to do that this basically is allowing us to have like static variables, right? This enables our functions to have state, which is something we're not supposed to have. But this doesn't violate our referential transparency, right? Because this is just generalizing, passing an extra parameter along, right? Which we were doing a lot before we even touched these state transformations, just saying this function, like for example, blockus, like one of the solution that I prescribed said, you should like just pass along like what blocks or what labels you were allowed to use, right? Blockus was saying, okay, I'm going to use a label from the set of labels and return the remaining labels, right? That was sort of having blockus have a state of the currently used blocks, right? So we did this, and you're doing some homework on states. We then took that state type and said, well, if the state that I am passing around is the entire status of the universe, then technically speaking, I can do state-based actions or actions which have sort of consequences, and that can be brought into the functional programming paradigm. And so this is something that's like technically pure or theoretically pure, but practically impure, right? Because the practical, well, we can't pass around the entire state of the universe. That's not possible. But so the way that we handle this in Haskell is to wrap it in this IO type. Because remember, as soon as something becomes IO, it's wrapped. And there is no way to take that IO wrapper off, like by design. But that doesn't mean that we can't have purity. And so all we've done is we say we have these like actually pure functions, these fake pure functions, and these fake pure functions, no problem, can call the pure functions. And you'll find that like sort of in practice, it's not that hard to separate the IO stuff from the rest. And like the rest is where like the meat is, right? The IO basically is just like the last thing that you'll ever need to do, right? Asking, okay, so what integer is the thing that I should manipulate here? Okay, so next week is nothing because we're done. That's it. Put a bow on it, wrap it up, pat yourselves on the back for a job well done. So I guess we have the exam coming in June, right? So my plan from here to there is like, I really want to get all the stuff graded, right? So you can check your grades, so you can complain to me that I've marked something wrong. I also want to provide solutions to all the homework I gave you, because now I have a little bit of time to write, and I'm going to try to get all like the unit test out to you guys. And again, come visit me in terms of asking questions. It's a lot easier for me to engage with you on the whiteboard instead of like typing out. Like when I type out a solution on Piazza, I have to be very careful about how I write these things. So I've had my 48 hours off Piazza. I'm going to try to engage with it again. But again, please try and write public posts to try to help one another, right? That's going to be helpful for you guys to prepare. So before I talk about Python, is there any questions now about like the exam or about like literally anything that we've done like up to this point? Because the stuff I want to show you in Python is just for fun, essentially. Okay, or just give me thumbs up to move on. Great. I also want to give a thank you for like you guys, the ones who are here, for showing up Mondays at 8 o'clock. This would have been a lot worse if I wasn't able to have this type of interaction with the chat. You guys made this not suck for me. If I had to sit here alone, right, and talk into a screen, this would have been a lot more wooden. It was nice to have you students along with me, sharp Monday mornings. I do really appreciate the ones who are here, right? YouTube, I love you as well, my YouTube students, but these ones, double thumbs up. Really gets me in the feels, guys, that you guys wake up on Monday mornings. I sure as hell wouldn't have woken up 8 a.m., especially given that the lectures were recorded. So thank you for being more studious than I would have been. Oh, I'm supposed to tell you guys to go and evaluate me, which will be helpful for me to improve my teaching. But if you give me 5 stars, that's actually going to help me. So I'm on probation technically, right? So they're trying to figure out like if they should keep me. After 2 years, they'll decide yes or no. So if you could go and give me some good rankings, that will help me keep my job here and get promotion so I can feed my family. So that would be appreciated too. I'll have to go onto the Piazza and put that link. Okay. Hashtag keep Paul at UQ. Yes, which is easy. All you have to do is fill out that evaluation and rank me high. I have to do the thing that the podcasters do and say, give me a 5-star rating. I've had a lot of like, oh, he's the best professor ever, 3 stars out of 5. So what the fuck? So smash that subscribe button. Go to the iTunes store. Oh, the advanced listing of Haskell. Yeah, I'll do that. Yeah, I should write that down right now. Post Haskell sheet. Yeah, UQC's 5 is average and everything else is bad, right? So I don't know. Help me work within the system that they set up. Okay, so can you see my REPL? Probably not. Oh, yes, you can see a REPL. Okay, great. So give me a second here. Okay, so we're going to be talking about Python now, which is great. I love doing these code context switches in class, but let's see how we go. All right, so get out of here, Haskell. We never need you again. So I've said this a bunch of times, but it's like never been my objective to make you students Haskell programmers. It's been my objective to force you into a language which would not permit you to do imperative programming, because nothing was stopping us from doing functional programming in Python. And I'll show you why. Why? Well, check this out. Foo is equal to lambda x y goes to x plus y. And let's see if this works. Python 3 interactive. Foo 2 3. All right. So you have lambda expressions in Python. So I guess the end, right? Therefore, you can do all the stuff that you did in Haskell in Python. But like, I'm not really even joking, right? Like truly, like you have a lambda expression. This now means that you should be able to get everything that lambda calculus gives you. Of course, we're not going to stop here, but you should appreciate it, right? That like what foo of 2? No, you can't do. You can't. Like I can't even type it in, right? Because this is not a curried function, right? This can't be partially evaluated. Whoops. Right, but Yeah, I know maybe that is a problem. Okay, but this is what I want to show you. If we need to bring in these things called function tools, and just I'm also going to bring in some extra typing information. List. Okay, so that's the first thing to realize, that like, yes, we have you have lambda calculus expressions in Python. What's the next thing I want to show? Mapping. Okay, we can do maps, right? So suppose I have a list 1, 2, 3. Let's show that we can do maps over this. Okay, so let's say y's is equal to map over x's. What do you want to do with this list? Maybe double it. Okay, let's double. So that would be a lambda x goes to 2 times x. Whoops, see, I'm typing like Haskell. So let's go back in. So y's should be a double. Okay, but we see the fact that it says this is a mappable object because Python's doing something a little bit smart, right? It's delaying the computation. It's saying, well, okay, you can give me a list, I can map over it, but that's actually just going to be a computation waiting to happen. Well, it's precisely lazy evaluation wrong. You know, that's what it's doing. This is smart, right? If this list is really long, like Python's saying, well, I'm not going to do this until I absolutely have to, right? You can stream from this list as much as you want. So if that's y's, I can always say for y in y's, print y. That should work. There you go, 246. But I can also convert this back to a list. Oh. So this is a nuance, right? Because doing this print here actually moved that stream to the end of stream, which is why that returned as an empty list. So if I get rid of this and go back in, we have y's is this. I could list y's 246. All right. Okay. So you have mapping. Okay. What's the next thing that we want to do? Maybe, oh, we don't have sections. No. Yeah, I don't even think we can call 2 times 3 2 times. Yeah, it won't even, yeah. So I don't know, it'll be weird now that like you'll be angry that you can't do some of the functional stuff in Python, but Python is getting pattern matching soon. Or you're going to be able to do stuff like as in input, rip off the head of the list and have the tails, right? So that's going to be coming in the next iteration of Python. So that will be cool. That will clean up code substantially. But like, let's do a filter. Right? And the thing that we need to remember about filters, so if I have x's like 1 through 100, that I can already do filtering via, oh, I can't do this in range to 100. I can already do filtering via list comprehension. So I can say x, oh, shoot, for x in x's. How do I get the predicate here? Oh, if, yes, if x mod 2. Thank you, guys. So I'm just going to say this is Z. Let's read this in. Great. So we have filtered out all of the even numbers. Okay, but let's show that like we can just genuinely do this with a filter. So this can be replaced with filter. I can say lambda x goes to x mod, I don't know, 3, and this is going to be taken from x's. So we have z's. It's a filtered object, so the computation has been delayed. We can do this, and there you go, right? So you have your maps, you have your filters, you have your list comprehension. We're doing pretty good. What's next? What's the next thing that you want? You want to do zip? Sure, let's do zip. Zip. Okay, so in Haskell, we had zip. In Python, we're going to have zip. So let's just see 4, 5, 6, 7. So if we zip x's and y's, let's call that z's. What do we expect this to be? Well, given that I didn't give zip an operation, it's going to have to be, well, this is going to give you a zip object first. That's what you need to note. Second thing is you're going to get back, what is happening here? A list of tuples. Right, but then over this list of tuples, right, you can just go ahead and like map like addition to it. X, Y goes to X plus Y over this. And then we want to take list over that. Oh, wow. That's because I pushed the pointer to the end. Psi, let's go back in. See, now we're grappling with sort of non-referentially transparent stuff, and things are already going to shit. Let's try this. What is going on? One required positional argument. Oh, right. Right, because I'm actually mapping over tuples here. So this is an X tuple, right? So how do I index tuples in Python? Okay, so let's see. If this is a tuple, then it's X tuple not. Oh, can I just take a sum over a tuple? Let's see. Oh, but again, I pushed the pointer to the end. Okay, perfect. Yes. So you have maps, filter, zip. Okay. Oh, does that work, Miles? Okay, let's see. I'm curious. So Miles is saying we can do lambda over a tuple like this and say this goes to X plus Y. That seems like pattern match. I'd be surprised if that worked. Yeah, you can't. Be nice. Like this is something that we could do in Haskell. And maybe this is something that we're going to be able to do as soon as Python brings in the pattern matching, but currently not. Good to know. Okay, so we have maps, we have filters, we have zips. What's next? What other higher order operations do you guys want? Give me one of those dirty for loops. You want a loop? No. Of course you have for loops, if statements, right? Drooling. Yeah, you guys get to use your while loops again. Ron wants to do an applicative functor. Get out of here. Come on, what are one of the higher order operations that we can expect? Bonads. It rhymes with olding. Maps, filter, zips, folding. Yeah, thank you, Lyndon Wells. All you trolls. Okay, so here's the thing about folding. It's not actually provided naturally by Python. It's like in this functools library. So I'm going to call this a fold. But what it's actually doing is calling this functools reduce. Now, notice how I didn't call it a fold left or a fold right. Oh, actually, okay, let's put a pin in this because you guys were drooling over for loops, and I actually have a for loop example here. So we do have min and max bound in Python. You may not realize this. So suppose I want to write a function which gives you the maximum, or yeah, gives you the minimum, right? So let's define something called minimum value in a list. So X is a list of integers, and you want to return integers. Jeez, small case here. Okay, how can you do this? Right, let's do this with the loop. Right, so but the problem is you'd have to do something like if not X's, then like return, I don't know, like something, right? You have to check if it's empty, right? Else we can say that the answer is like one thing in the list, and then say for X in X's, right? If X is greater than answer, then answer gets X, and then return answer. Like this is an imperative thing that you're used to doing. But like what should go here, essentially? I don't know, like maybe error, maybe like nothing, right? I think we have nothing or none. Yeah, none. Oh, less than. Okay. So this is a typical imperative thing. The first, if it exists, yeah, maybe. But this is what I want to do instead. Like, screw this check. Okay. I'm just going to set answer to minus float infinity. And this will work, right? Because if there's anything in this list, it's definitely going to be positive float infinity, less than infinity. And so let's give this a go. Whoops. So minimum of 1, 2, 3. 1, minimum of 1, 1, minimum of empty, infinity. Right. So the fact that you can use these boundaries, right, on data types, it's super useful for eliminating like a bunch of edge cases. Right. I've trained a bunch of people at interviews, right, at like sort of in industry. Using this is really helpful. Like, so I've been trying to train you to understand that base cases, if you can use the boundaries of the data type, will simplify things quite a bit. Right. And it does make sense for the minimum of an empty list to be infinity. If you think about it like this, right? The same reason that the sum of an empty list should be 0. Because that's what it needs to be for like the recursion to work, or in this case, for the sort of algorithm to work as a whole. So there you go. There's your imperative example. Okay, so back to folding. Okay, so notice that I'm calling this fold and not fold left or fold right. Okay, so let's see what this is doing then. So I have to find my example here. Okay, so I'm going to define add like this. So it's lambda x and y goes to x plus y. Let's also define subtract to be a lambda x and y to be x minus y. And then let's fold. Okay, let's define x's as 1, 2, 3. Y's as, well, I don't actually think we need a y's. Okay, so let's fold add over this. Let's call that Z. Go out, back in. X is not defined. Oh, X is. Okay, so if I look at Z, I get 6. So clearly that's what we expect a fold to do, right? I expected this to do something like 1 plus 2 plus 3, although we don't know which way the brackets work. Okay, let's replace this with subtract, right? Because let's determine if this fold is doing a left fold or a right fold. So what are the two options here over this? Well, it's either 1 minus 2 minus 3, or what's the other one? It's going to be 1. Oh, hold on. So that's stacking. I'm going to add one more here. So this should be minus 3 minus 4. So that would be, the right fold would be what? So 3 minus 4 is minus 1. 2 minus minus 1 is 3. 1 minus 3 is minus 2. And then, okay, Saxon, everyone is to ignore Saxon. He's being ignored. Ignore me. Okay, or the other one is this. I should have 2 brackets. So it should be 1 minus 2 minus 3 minus 4. Okay, so that one's going to be what? 1 minus 2 is minus 1, minus 3 is minus 4, minus 4 is minus 8. Okay. Is this the left fold or the right fold? Which way are the brackets stacking, Ron? Right. Yeah. And this one is what? Bracket stacking to the left. Okay. So if I go out and go back in, and I ask for the value of Z, this is going to tell us if it's left folding or right folding. But you see how I had to pick an operator that wasn't commutative in order to suss this out. So Z is neither. God damn it. What did I do wrong? Did I save? Good question. Leon, you're my hero today. -8. Okay, so you see that this reduce or this fold that is implemented in Python is actually doing a left fold, but we don't have sort of the base operator, right? But you do have a fold, so to speak. Right? It's just called, so a fold without a left or a right is usually the one where it's saying, like, we're not going to take a base operator, right? So you can't fold over empty lists, or you shouldn't be able to fold over empty lists. I have to give a function, add. Right. So in Haskell, if you were to fold over something empty, it knows what to do in that case. It just returns the second variable. Okay. What next? So we've done zips, we've done folds, we've done maps. I guess what's left to do now is higher order functions. Functions. I don't think so. Right? I don't, or it may, I just don't know. But if you look up like folding in Python, it usually just returns this reduce. Like you can write folds in Python, and you should think about how you can do that over lists. But I think it doesn't make sense to like write fold in Python because that's pretty inefficient. Anyways, this is not a Python course. If the optional initializer is present, oh, so if I put something in this reduce, it should work. Place before the items. Okay. Argument 2 must support iteration. Okay. Thank you. Okay, so you can get it. Okay, but now we just have to figure out if we put one more thing here. If I put a 5, then that should be minus 13. Okay, let's try. No, minus 5. How did that work? So how did this 5 interact with this minus 8 to get minus 5? That doesn't make much sense. Okay, let's pare this down. The initializer only works in empty lists. Yeah, but it actually changed my result. So if I do fold over with subtraction over x's, I get minus 8. If I add a 5, it changes to minus 5. Now I'm curious what this is actually doing. Okay, so if I fold, let's fold over one thing, 0. And let's subtract 1. That is, what is this doing? Okay, so that's 1 minus 1. Why should that be positive 1 and not minus 1? Oh, it's putting it in the front because it's a left fold. Yes, that makes sense. That makes sense. Okay. Right, so going back to this one that I didn't understand. This put a 5 as the first thing. So it'd be 5 minus 1, which is 4, minus 2, which is 2, minus, yes. Okay, great. So it seems if you get functools from Python, that you do in fact properly get left fold. But practically speaking, you usually need reduce. Okay, so that's good to know. 20 more minutes. Okay, higher order functions. So what was something that seemed miraculous in Haskell was that we could have functions which accepted functions and returned functions. I'm saying this is also the case in Python, right? Nothing saying that the thing you're returning had to be a constant. Like we can in fact have functions that return functions in Python. So let's look at that. Okay, so first let's do a function which accepts a function. So say this is a function called bar, which takes an integer to an integer. And let's just say that it triples it. So return triple x. And suppose we also have a function called foo, but this foo is going to accept a function now. something is screwed up in my, okay. Let's just say this takes spam, a function, and returns an integer. And what's the spam going to do? I'm going to return spam 7. Let's see if that will work. Okay. So if I give foo bar, what should happen? Well, foo takes bar, and then it calls bar 7. So this should be 21. But there you go, right? This is a function which took a function as a parameter and used it. Right? So that's one thing that you should know. Nothing stopping you from passing functions to functions, which shouldn't surprise you. Like, this is not something that was excluded by the imperative paradigm. Right? You can do this in C, right? You just pass a function pointer as the thing that you want. So that shouldn't be too miraculous. Okay, so this was what? This was a functions, taking functions as input. Okay, so now we need to do the other thing, right? Functions, returning functions as output, okay? Okay, so I can have something like foo, which is going to take an integer, and it's going to return a function, which I don't really have a doc type for, so I'm just going to leave that. I think that the doc type is technically something called callable, something like this. Let's see if that will allow me to do that. No, you guys can look it up. I was going to take that out. I think it's called callable though. So I was going to leave this out. Okay, so I want a function that returns a function. So given x, I don't know. Okay, so let's define bar. Right? So I'm in a function defining a function, which takes an integer. And what do I want to do here? I say maybe I want to return x plus y, and then foo just returns bar. Okay. Or maybe not x plus y. I'll say x times y. I'm generalizing bar, which is just returning something. Okay, so let's go out. Let's go back in. So I can say I have a function spam, which is going to be equal to foo when I give it, I don't know, 7. Right. So spam should now be a function which given a number, triples it. Or 7 tuples it. Well, there you go, right? Here's a function that took a parameter, wrote a function, and returned that function. And so that's pretty cool, right? That the fact that, like, you know, you do have higher order functions in Python, like this kind of stuff can really simplify things, right? You can, or sort of instantiate custom made functions. Okay, but that's not the reason. That's not the main thing I want to show you, right? So now that you can have a function which takes other functions and returns other functions, you can start writing, like, you can take the Haskell sort of notion here and say, there's a pattern here that I apply like all the time. Yeah, decorators. Decorators is exactly what I'm trying to get to. So there's this thing in Python called a decorator. And I want to show you how those decorators work, because it really significantly increases the clarity of your code if you can use these decorators. So decorator. So decorator essentially is just a function which takes a function as an input and returns function as output, which has a special sort of syntax to call it. So let's take a function. I'm going to call it make pretty. And this function takes a function called function and defines another function which just prints I got decorated. And returns a new function, or returns a new function, which is taking the old function and just adding one extra line. Okay, inner. Now let's define another function called just ordinary, which accepts nothing, which is just going to print I am ordinary. Okay, so let's go out. Let's go back in. Okay, so I have this function ordinary, which I can call with no values. That just says I am ordinary. I can make a function called special, which takes make pretty, gives it ordinary. What does special do? Well, it does everything that ordinary used to do, but adds that one extra line. Okay, so that itself is not the interesting thing. The interesting thing is this. If you have a function which takes a function and returns a function, there is a special way that you can invoke it. And that's like this. You take this @ symbol and you can say make pretty. And what does this do? Well, this is going to take this and wrap this function like that and return it, but it will have the same name. So I'll show you what I mean here. If I go back into Python and now I call ordinary, it will print both things. Right, so this is like, this is interesting, right? Because it processed the function, but then you get to use the same name back with this extra functionality. Like that, it's cool. I think this is very cool, right? That you have this special decorator type of syntax to sort of add extra functionality to a function without changing its name. Now, what is like one of the most important use cases for this? Well, caching, right? I mentioned that if you, can you pass additional arguments to the decorator? I don't want to get into it. You can look it up, right? This is your entry point. I don't know if you can pass more stuff to the decorators is my answer. I haven't really studied them that much. I just know, I know how to use them, right? When I need them, but I don't write custom ones. Miles says yes, right? So someone can dump that spec, but yeah, I just want to do this caching to show you, because I mentioned that once you have non-linear recursive functions, that the exponential nature that they sort of call is a problem. But the solution to that problem is caching. Okay, so let's look at caching in the last 10 minutes. So I'll give you an overview of what this is. I'll show you the pattern that we want to invoke. So if you have this Fibonacci sequence that sort of looks like this, right? So Fibonacci numbers, if n is less than 2, then you just return n. Yeah, caching is, well, yeah, memoization is like a synonym for caching. Yeah, exactly, Lyndon. That's what we're going to work to. Okay, so I have this function, and then otherwise it returns the sum of the last two numbers. So let's call this in. Okay, so I can get like fib of 10. Maybe I can even get fib of 20. But like as soon as I start doing something like fib of 100, gears are spinning, right? It's computing. It's trying to go, right? So what do I want to do instead? So we're going to leave this running. I'm not timing it or anything, but let's just see if it can even finish its computation by the time I write the cache version of this. So I'm saying if instead of doing this, we gave fib, I'm going to call this dfib for dynamic fib. We let this have some type of cache. So I'm just going to call that cache H, and we can play some tricks here. So this is a dictionary, and into this dictionary, I'm just going to dump these two values in, which are the initial conditions, right? Which are basically going to handle the edge cases. And I'm going to say, okay, if the input has already been calculated, if it's in this cache, actually, maybe I should just call this cache. If n is in the cache, right, then just return the cache value. Like there's no need to compute it again. Right? Otherwise, let the cache at this value be equal to dfib of n minus 1 plus dfib of n minus 2, which are going to be calling into the cache, and then I'm just going to return the cache. Okay, so take note that this Fibonacci of 100 is still computing, right? It hasn't finished. I'm just going to terminate it. Let's go back in. I'm going to call dfib of 100 now. Remember, like I wrote this function while the other one was working. Boom, instant, right? So adding that cache was extremely important in terms of the computational complexity of this. Well, I've gone from like waiting so long that I could actually go and implement the cached version and run it before the other thing finished. Okay, so what I'm saying is that adding a cache in this manner is an extremely common pattern, right? So we can actually abstract this away by writing a function or a decorator called memoize. Now, memoize is just another term for caching. So what do we want to do to memoize a function, to give a function a cache? Well, again, I want to instantiate a cache, which is just going to be an empty dictionary. And then I want to return the memoized function. And I have to do something here called args. So there are two things that you can call within a function from Python. Pointer to args, or pointer to sort of optional arguments, KW args. But in any case, this is just a way of saying whatever arguments function was called with, I want to use them. So the key is going to be what I called n here. That's going to be called args. And I can say something if key is not in the cache, then return, or I guess I want a cache key is equal to the function at hand called with its arguments. And then I want to return the cache at the key. And then after I want to return the memoized function. Okay. So now I can have something like, let's define a bad Fibonacci. I'm just going to grab that. Where's my Fibonacci? Here. Okay, let's call this bad fib. Let's go out. Let's go in. Okay, I'm just going to call bad fib at 100 to show you that it's inefficient. Okay, let's stop that. Let's go out. Let's add this memoize to it. Let's go back in. Let's call bad fib at 100 again. Instant, right? So we wrote this decorator, right? Which in Python has this neat provision for like adding functionality to a function and allowing you to use its name again. Wild. I know these decorators are amazing, right? And furthermore, you can stack them. Right? If you want, you could apply several decorators, right? At the same time, right? An arbitrary number of decorators, right? But this memoize one is super useful, or the one that Lyndon Wells dumped in the LRU cache, right? That's going to even be faster. That's telling it, look, I want you to cache, and not only do I want you to cache, I want you to use like very fast memory to do this caching. But this should be easy for you to understand now, right? These decorators, right? Because you should be more than used to the fact that like functions can accept functions and return function. That's all we've been doing all semester, right? Is passing around functions. So again, if you look up like what is functional programming, you may get the response. Functional programming is a type of programming where functions are considered first-class objects, right? Where we do not choose to distinguish between functions and like any other type of data. Right. So I hope what I've taught you this semester is going to stick with you and make you better programmers. And in particular, make you less afraid of using recursion as a tool. Right. That's all I want for you to do is take the recursion tool and put it in your toolbox and be confident to take it out and to use it. Right. There are times when the simplest solution is going to be through recursion. And I also taught you how to like take inefficient recursions and convert them into efficient ones, right? If you're worried about winding steps, you now know that you can convert those into tail recursions. Or now you know that in Python, you can, right, do this type of memoization. There are tricks, right? I don't know if it's possible to write a decorator which takes a primitive recursive function and converts it into a tail recursive one. That would be an interesting question. So that's it. We are done. I don't know if I'll ever see any of you guys again in class. I hope I do. Some of you are in lower years here yet. Those of you who are graduating, I wish you the best of luck in your future endeavors. Please come visit. Can you dump that script into the chat? Sure. Oh, it's not letting me paste. Okay, hold on. Just grab the file itself. If I can find it. There you go. So I ask if there are any final questions. I'm going to try to leave my door open or if it's closed, just knock. I'm going to try to be here as much as possible. And I'm especially going to be here like in the days leading up to your exam. But okay, so again, projects I think are due at the end of the week, right? Focus on the written part. I can probably unofficially say I'm not going to run the grader, auto grader on the code until Monday, like bare minimum, right? So unofficially, you have till Monday, right, to submit the code. Any final words? Oh, thanks you. Thank you guys. It's been a blast. Hope to see you guys again. Thank you. Thank you. Thank you. Okay. Go and into the world and program. And I'll see you guys again, hopefully someday. Signing out, YouTube. Smash that subscribe button. Peace and love.